Okay, so I'd like to thank the organizers for inviting me to give this talk. It's a pleasure to be here. I'm going to present today work done in collaboration with Hendrik van Uiten, who's now a faculty position in Bath in the UK, Paul Duffel, a very talented postdoc now at UC Berkeley, and my current students, Jeff Ryan and Yiyang Yu at NYU, as well as my former student, Jonathan Zrake at Stanford. And I'm going to mention simulations attempting to understand the afterglow of gamma ray bursts as they are connected to the central engine producing GRB. And everyone's familiar with the pre-Swift story, which was a broken power law with a jet break time, which was of interest. And Jeff Ryan, as I'll show you later, has done a very nice job modeling the exact shape of that jet break in order to understand the structure of relativistic jets. And the basic story, of course, is that initially you're so relativistic that you only see a small patch of the emitting region. But as the blast wave slows down, eventually you start to notice there's no material that's radiating to the sides of the jet, and you get a steeper rate of decline. And what I'm going to show here is that that's really the cause of jet breaks in the late afterglows. Okay, but another really interesting thing is that you might have predicted that the early slope would go to very early times, and that's not what's found by Swift. So Swift found a very different type of behavior where the early afterglow is declining quickly and then forms a kind of plateau. And I'm going to show you some interesting clues that this may give us about the central engine of GRBs. Okay, so the basic story, just to give a cartoon picture, is that we have many orders of magnitude and length scale to understand. From the central engine, which it can be a star, or the ejecta cloud around a merging binary system, but it produces some sort of relativistic beamed outflow, which eventually decelerates by driving a shock wave into the ISM, which radiates synchrotron emission, which we observe. So there are many interesting components to this puzzle. The first is this, which involves the breakout of a relativistic jet from its ambient medium. Then a kind of coasting phase where it decelerates and stops. And then, which I'm going to call the early afterglow phase. And then there's the late afterglow phase where all of the energy is in a collimated shock wave that's traveling through the interstellar medium. Okay, and this is kind of like this. This is an Earth-based version of this picture where you have an explosion, let's see, of some sort, but maybe it's not going to show. It's too bad. Uh-oh. It's a failed GRB, yeah. So, yeah. So let me just see what I can do here. Maybe I can show it to you like this. Okay, there you go. And here's the key thing. There's an explosion, but look, now there's a blast wave traveling through space. And here's the ejecta, and then there's some late engine activity. So there's all this kind of messy stuff, but then at some point it's transferred into this blast wave. So, sorry? Sure. Let me see if I can actually do it like this. Yeah. So there's this explosion, and then it drives this shock wave, which you can see because of the index refraction of air. And then at late times, this was a rocket that was supposed to launch, but it didn't. It exploded. So what I'm going to say is that GRBs are basically a relativistic version of this thing. And one of the things that isn't certain is that when the jet break happens, it's also thought, because the jet has decelerated, so its opening angle is 1 over the Lorentz factor, that all of a sudden it discovers lateral space and it can spread sideways dynamically. And that was another hypothesis for why there might be a jet break. And I'm going to show that that's not what happens. And so we did this by a couple of years ago, showing simulations of what happens when you start with a relativistic jet. And this is the Blanford-McKee solution, which is in the late afterglow phase. So the engine was down here. It launched a relativistic blast wave into space. And the technical challenge from a numerical simulation point of view is that all of the energy is in an extremely thin shell of width r over gamma squared in the very front of the shock wave. So if we change the stretch, you'll see that that's what we're trying to simulate, a very thin structure traveling at the speed of light through space, sweeping up the ISM, and then we're interested in how its dynamics spread laterally. So it's very hard to resolve this, so we use many levels of adaptive mesh refinement. So basically you put at least 20 zones across this, and this is the initial opening angle. And so here's gamma is 1 over theta, and so that's when it's supposed to spread by the common story. We don't see that. That doesn't happen. It just keeps on going, and it stays beamed much longer than we would have expected. And then a little bit later, there's another estimate of when a different model predicted that this thing should spread sideways. And even then, right here, it doesn't. This is a model by Waxman. And then it keeps on going for much longer than you'd expect. And then at very late times, this thing starts to spread. And you can start to see that process. It starts to move sideways and so on, becomes quasi-spherical, trans-relativistic. And then at very late times, it's going to approach the set-off-Taylor solution, which is just a spherical, non-relativistic blast wave in space. And you're going to see that happen in a second. And then we'll zoom out a little bit so you can see these two lobes that look kind of like a peanut. And then eventually, the two lobes merge at the equator, which may produce some late afterglow signature and so on. And then eventually, you transition to the set-off solution. So here you're trans-relativistic and beamed, but later any point explosion will drive a spherical non-relativistic blast wave at late times. And so this is what that converges to. So very different from the kind of predictions that had been made. And let me admit that I was a little, and so the basic prediction was that at the Lorentz factor, 1 over the opening angle, a jet, which was initially beamed, should all of a sudden spread sideways. And we're not seeing that. So the question is why? And I'm going to show you that the culprit here is not this, it's this. So it's the equal sign. It's not exactly at this time. And that's what we learned from doing numerical simulations. So first, let me show you, the reason I was a little bit hesitant at first was that this is very challenging to do. And you can see whenever you set up Blanford-McKee, there's a little bit of a transient that lasts for a little while. And in the lab frame, that transient, this is the Lorentz factor as a function of time, that transient lasts until the Lorentz factor is about 4 or 5, which is exactly the time when you want to see the spreading. So it's a little bit hard to trust that thing. But recently, I've been able to do these simulations in a boosted frame. So I just boost along with the jet and fully resolve things at Lorentz factors of hundreds, even thousands at times. So what's really good is that transient goes away when the Lorentz factor is several hundred, so still much more relativistic than the 1 over the opening angle of the jet. So we can really trust these numerical simulations. So that's the new thing, and this is a paper that's about to be submitted. And so this is what we see. So, and this we can believe. That this, for sure, this thing, 0.01, that 1 over that would be 100. So you'd expect that to spread at 100. Doesn't. This is Blanford-McKee. It spreads at 24. Okay? So it's later. It does spread eventually, but you have to be able to resolve really high Lorentz factors. So it's technically challenging. And we did this for a bunch. We went all the way up to 0.001 radians, a very narrow, ultra-relativistic jet, starting with Lorentz factor 1,000 or so. But notice something that everything that had been done previously were for 0.1 radians and 0.05 radians. The really important thing to notice is that when they transition away from Blanford-McKee, it happens at Lorentz factor of about 2 or so. So it's no longer in this ultra-relativistic phase, it's in a trans-relativistic phase, and that's why you get a different spreading. We now, in a boosted frame, are able to go to narrower, more relativistic jets, and we find that the spreading happens at 0.24 of 1 over theta. So that's the thing that we can see, and we can see here, this is the rate of change of the Lorentz factor as a function of time, and what we see is in all these ultra-narrow, ultra-relativistic jets, we see this really fast deceleration. Whereas for jets that we expect in GRBs, 0.05 and 0.1 radians, you don't really see that. As soon as it tries to go to this exponential spreading, it immediately transitions into a different phase, which is trans-relativistic. Okay. Yes, okay. So here's what we find. The Lorentz factor, when the jet spreads, is not 1 over theta. It's 3 minus k to the minus 1 times 1 over theta. And that k is the power law index of the ambient medium. And what I just showed you, and we can show this analytically, that the Lorentz factor is 0.24. And that's the difference. So if you have so for the a 0.1 jet, you might expect it to spread at 10. It spreads at 2.5. And for a 0.2 jet, it spreads at 1.25. So it's really trans-relativistic. So that's the mystery that I think we've solved now. And now we can look very carefully at this, and this is energy density, and this is Mach number in the lateral direction, in the theta direction. And what you see at gamma of 100 is that the core of the jet, where most of the energy is isn't spreading sideways at early times because it can't. It's too relativistic. And this is fully resolved. We started Lorentz Factor of 400. And then here is that prediction of 1/4 1 over theta. And you can see the rarefaction wave has just reached the axis of the jet, and now it's starting to spread sideways, and this picture makes sense. It does not, however, agree with a model by Granat and Perron, who had this trumpet model. We still differ from them, at least that model, but I think these are now fully resolved and fully trustworthy. Okay, so why is this interesting? The dynamics to me is interesting in and of itself, but we can also solve the equations of radiative transfer through this expanding, laterally spreading, transitioning hydrodynamic blast wave as it travels through space. And we solve all the time slices of that dynamics, and then we can calculate what an observer would see as a function of time. And the key thing is not just for an observer on axis, which was basically no one. There's much more solid angle off to the sides, so we can draw planes through the simulations and calculate what an observer would see at any angle, including completely off axis, but also for viewers who saw the GRB, but most of the people who saw the GRB are seeing it from near the edge. So that turns out to be very important. Oh, sorry, okay, I'll stay here. And so this is what we did. We showed this a couple of years ago, and we found from the X-ray to the radio, we got these types of light curves. So even observers on axis see a diminished jet break that's pushed to later times. And off-axis observers see some very faint things that disturbingly have still not been convincingly detected. Okay, and then just to show more clearly what happens, here's the same jet, and here's the radiation calculation if you're on axis. Here's if you're halfway to the edge of the jet. So you see the jet break is like what's much smoother and much later. And then here, where most observers are, it's pushed to very late times where you may no longer be observing. So this can explain the reason you actually wouldn't naturally expect there to be breaks if you could take into account that most observers are viewing gamma ray burst jets off axis. We're able to use scaling relations, which I'll show you in a second, to generate millions of light curves for all possible GRB jets by scaling, by using dynamical similarity in order to fit all the parameters of the gamma ray burst. And this is I band, R band, V band, X-ray, and then also in the radio simultaneously. And we're able to get some parameters of the explosions which are new. And what's really cool is that we don't have to do a new simulation every time. We've already done all those simulations. And so we can create light curves by exploiting these scaling relations. In other words, we don't need a radial coordinate, we just need a dimensionless radial coordinate and a dimensionless energy and density. And once we do that, we can take the same simulation and scale it to any energy, and it has the proper limiting cases in Blanford-McKee and Sedov-Taylor. And so here's a simulation we didn't need to do. Because this one, we did at 10 to the 51 ergs, 5 times 10 to the 51 ergs. We did this one thinking we needed to cover all of energy space, but we didn't. We just need to rescale space and time. And you can see every single wiggle is the same. So one jet simulation can be scaled around dynamically. And this is put together in a code called Boxfit. So you can put any radiation on top of the dynamics there. And so we don't, we can just use this set of simulations to fit data. And so we don't need to do any more hydro simulations anymore. Here's the most surprising thing, and I've shown this before, but the radiation itself scales. So we don't even need to use Boxfit, we can use Scalefit, which Hendrik van Rooten is putting together right now. In other words, this is a 10 to the 48 erg explosion, and it's light curve. So you save 5,000 dumps of a very expensive hydrodynamical simulation. You calculate all the radiation at any angle, and you didn't need to do that. All you needed to do was rescale the characteristic frequencies and overall flux of this higher energy explosion, and then you're set. So you can wiggle around this curve in space and use a Markov chain Monte Carlo approach to fit all gamma ray burst afterglows and get distribution functions for all of the model parameters versus everything else, and you can learn something. So here are the model parameters. And we get corner plots that look like this. It's a little complicated, but here are the data for 110422A. And here's E iso, the density, the opening angle of the jet. And here's the observer angle with respect to the opening angle of the jet, the electron slope, and epsilon E and epsilon B. You can see some things are not well constrained. They have wide distributions, but others are. And in particular, this one had a very well constrained jet opening angle, and the observer was at 0.6 of the opening angle of the jet. So you're really seeing these things not straight on, but edge on. And that makes a big difference because it reduces the inferred true total energy and reduces it by about a factor of 5 or so. So it's within the maximal energy you can get from a spinning neutron star, and this type of data does not require black holes for the formation. Okay, here's a zoom in showing that for this burst we get about 0.05 radians, and look, a really well-constrained thing, which for this burst is 0.65 or so is the viewing angle. And here's electron slope. So we've done this for all swift bursts that had good data and redshifts, and we found this kind of distribution for the observer angle. So it's mostly near the edge as you'd expect. The data isn't as good if you're near the edge. So this, so basically the conclusion is there's data-driven evidence based on numerical simulations of GRB blast waves that gamma bursts are observed off-axis much more often. It's basically never observed on axis, and people should take that into account. And this is interesting for the electron slope. We can also fit this really carefully, which is of interest for plasma physics things. And all of this has been available on Afterglow Library at NYU. If you're interested, you can look it up there. And Boxfit and Scalefit will be available there. Okay, so that's the late Afterglow phase. I now want to discuss a really interesting transitional phase, which is when the jet interacts. So normally it was assumed that you kind of got internal shocks from a jet. It dissipated and then immediately formed a blast wave. So you transition quickly to the external shock. But that's not so simple, really, because what really happens if you have a forward shock, and this is the ejecta from the engine, sweeping up the ISM and transferring its energy to the shocked ISM. But you know the shocked ISM is less dense than the ejecta. So this is famously unstable, right? So you have what's called the Rayleigh-Taylor instability. You can't push a dense fluid with a light fluid or decelerate a dense fluid with a light fluid, and you get Rayleigh-Taylor fingers. So this is really important, it turns out. And this is the type of thing that Paul Duffel calculated a couple of years ago, which is really interesting and important. This is the ejecta, the brown, and this is the ISM here, and this is the density. And what we see is that there's a lot of turbulence driven by the Rayleigh-Taylor instability, which is trying to make its way to the shock. It's kind of infuriating. It gets closer to the shock at higher Lorentz factor, but then the energy is more compressed in front of it, so you never quite get there in this case. But this is for adiabatic index of 4/3, which is appropriate for a relativistic gas. And what you see is these mushrooms become skinnier and skinnier, and they're trying to make it, not just like cosmology, they only have a causal horizon, which is 1 over the Lorentz factor, so they can only grow small angular scale. So this is really interesting relativistic hydrodynamics, which is qualitatively new. And this is made possible by a code that Paul Duffel wrote, which is Lagrangian in the radial direction. So it follows this very thin shell very accurately. Okay, but that was for 4/3, and this shows a movie of what happens, hopefully. Looks like movies are not happy today. So let me just try this again. Okay, so you'll have to see it this way. But here's the blast wave, and you can see this very thin shell. And since the grid is moving with the flow, we're in Lagrangian space, you can see the growth of Rayleigh-Taylor instability in this really thin shell that would have been impossible to simulate otherwise, okay? So that's what you saw before, but then we realized that this gas is emitting energy. These blast waves are not adiabatic. They're emitting synchrotron radiation and also accelerating cosmic rays. So the gas is effectively squishier. If you increase its density, the pressure doesn't go up as much as it might have. And so we kind of faked that to some degree by lowering the adiabatic index. So everything else is the same as in this simulation, except the adiabatic index is 1.1 as a way to mock up the effect that the thing is non-adiabatic. And what we find is really interesting. In that case, the shock wave is corrugated constantly and constantly turbulent. And why that's important is that all fluids have what's called a small-scale turbulent dynamo. And if you have kinetic energy of turbulence, it'll wind up magnetic field lines into equipartition with the kinetic energy density of the turbulence. And what you end up getting is something like this. And this is a really beautiful simulation of relativistic turbulence that Jonathan Drake did. And you can see there's all these ropes and so on. And what this is doing is amplifying magnetic fields. So you don't need to assume an epsilon B, right? This is self-generated magnetic fields, which removes a free parameter in the afterglow modeling. More recently, Yi-Yang Wu at NYU, current student, is doing this not for the adiabatic case or the 1.1 case. He's doing it for synchrotron cooling. So he has a cooling here, and what he finds is that for certain combinations of the model parameters, he gets blast waves that are affected, so this is the adiabatic case, And the main thing that happens is the reverse shock is pushed back further, and the contact discontinuity is really gone. It doesn't exist at all. There's just a mess. And so this is what he sees. And for some low values, the shock isn't distorted. But for higher values, the shock is starting to be distorted. That's important because if the shock front is corrugated and it's relativistic, it'll stay that way. And if you're in that shock frame, the ISM is coming at you, you'll get shocked and you'll generate vorticity, which will perpetuate turbulence and perpetuate the growth of magnetic fields in the outflow. Okay, the last thing I'd like to discuss is the breakout of the jets from stars. And so we've seen things like this before. This is an old picture, but so no movies are working. Great, okay. And the jet breaks out, and basically we've seen this kind of picture before. Let me move on. The basic point, as has already been shown, is in 3D. This is a simulation by Zhang Wu's Li and Hager. In 3D, the jet kind of wanders back and forth, and there's material that's not relativistic yet, which is pushed ahead of the jet. But look, right when it breaks out, there's still a thin sheen, or whatever, sheath, of less relativistic material ahead of the jet. And that's inevitable, I argue, because as the jet is moving through the star, it's always got stuff ahead of it which falls off when it's in the star, because that's not relativistic. But when the jet breaks out of the surface of the star, it accelerates, and all that material is stuck in front of the jet and has to stay there. You really can't avoid that. So using JET, which is the relativistic MHD code that Paul Duffel wrote, that moves with the flow, we were able to explode a massive Wolf-Rayet star, low metallicity, 18 solar masses. And this is what we did is took the engine inside the star. So this is at 10 to the 7 centimeters, but it's Lagrangian, so this thing is expanding by many orders of magnitude. You'll see the radial lines coming through. And what you're seeing is Lorentz factor on the right and density on the left. And what's happening is you're getting the shell, but now the star is way down here, but now we can remove it. We don't need it anymore. And we can keep on going and follow this jet, because it's no longer in causative contact with the central engine. So now it's coasting. So this is a self-consistent simulation from inside the star, breaking out of the star, coasting, sweeping up the ISM. You can see it's becoming Rayleigh-Taylor and still unstable there if you have good eyes. And then eventually sweeping up the ISM and producing afterglow radiation as it drives a shock into the ISM. So we can, from that, discover a very interesting story. So here you have the jet at the center of the star, which is put in as a model, but a model with just a few parameters that we can constrain by observations. Breakout from the star, coasting, and eventually afterglow phase. And the basic dynamics in a cartoon form is that the jet breaks out with stuff in front of it. This is optically thin. Internal dissipation in the ultra-relativistic jet goes through there, but then eventually, this is both moving at about the speed of light, but eventually they collide. The shell is accelerated, the inner part is decelerated, and then you have amalgamated slower jet, which plows along at constant Lorentz factor, driving a shock into the ISM without decelerating until much later than you'd expect if it had been the gamma 100 stuff that was decelerated. And this is really close, so this is fully resolved. We see the acceleration all the way up to gamma 100. We see coasting with that cap in front of it, and then the collision with the cap, which produces a very rapidly declining X-ray declining thing. Then you coast, but you coast longer, and then you go to Blanford-McKee. Okay, so this is really important for the following reason, is that if you calculate synchrotron emission from this material, you get this sharply declining spike, then you get, you're shocking more and more material at gamma 30, and you have more and more volume, so this would be rising in fluence, unless you're in a wind medium, which we think you are. So if you're 1 over r squared, then you get a slightly declining thing like that. And this just comes directly out of the simulation. Then at late times, you go into advanced phase. So we could have predicted plateaus easily, and we should have, but we didn't have the capacity to follow this early jet dynamics, the early afterglow dynamics. And this is a GRB below it, rapidly declining plateau afterglow phase. Doesn't come from the engine doing anything special. It just comes from the dynamics and radiation properties of a relativistic jet interacting with itself and then with the ISM. So there are some predictions that this makes, which can be checked. It differs from predictions made by the internal-external shock model, which can be checked with data like these. The next thing that's relevant for this is that even ejecta clouds around merging binaries drive winds before the black hole forms and an accretion disk forms of just a few hundred kilometers, and this is from numerical relativity simulations. So just like in a star, this cloud helps to collimate the ejecta. And what we notice is that the ejecta cloud is not spherical, it's actually oblate because of angular momentum. And what happens is that helps to focus the jet and is really important. So just like with a star, an ejecta cloud can help, and what this means is that wide jets can be collimated by propagation effects, and you don't need a very narrow MHD collimated jet. Even something kind of wind-like can be focused into a jet for short gamma ray bursts. Okay, so I'll leave it there.
What do you assume is the composition of the ejecta?
This is all hydrodynamics, so it's basically relativistically hot gas.
No, I meant ions.
Sorry?
I mean, if it's a Wolf-Rayet star, then it should be ions. Do you assume it's just protons and electrons?
Yeah, so for currently, it's just a gas that has a density and a pressure.
It is getting interesting now you to actually look into the chemical abundance of the ejecta itself. It's not hydrogen at this point. And once you're now monkeying around with gamma, there are other emission mechanisms. Ions will open up. So it might be interesting to look at. And another quick question I had was to change your gamma from 4/3 to a little less, and you want to squish it away. Have you checked that you can actually radiate all that energy away?
Yeah, so that thing that I showed you, the most recent stuff by Yi-Yang Wu, does that. It uses synchrotron emissivity instead of a squishier gamma. So yeah, and it's found that depending on the parameters of the problem, so the energy and the density, sometimes you can get this, but not always. So there's only going to be some parameter regime, and so we're working on that right now.
Radiation can escape.
Yes, it can. Yes.
Andrew, so the transient that you showed from the numerical calculations that you push back to higher gamma, what is the source of that? And are you sure that any memory of that transient isn't contaminating results of when it starts to spread?
No, I'm not sure. The most interesting thing to do is, like I showed, is to start in a star, have the jet propagate through the star, push just the whole thing, push the stuff in front of it, generate Rayleigh-Taylor instability, then spread sideways. And as you can see, we've started to do that. We haven't applied the really good radiation yet to the full hydro simulations that start in the star. We have kind of a simple synchrotron model, but that's where we're going.
Yeah, so I was going to ask, so in your picture for the plateau and try to explain the steep decay in the plateau. So to be clear, so the steep decay is actually part of the forward shock in your picture, which I know is sort of not the standard orthodoxy. So I was wondering, in many cases you do seem to see the prompt emission sort of connect smoothly onto the steep decay. So I'm wondering, how you address that.
Yeah, so I would rather claim right now that the plateau is very natural. It so happened that this came out. We did not expect that, but it does come out. It comes out in part because the emission region is flatter. It's not spherical, which would make it hard to get such a steep decline, but it turns out, and so this needs more work, but this was for free. This was not, essentially, this is what we would have gotten without knowing about plateaus or anything, or what decays, steep decays. It's what we get.
So your approach is pure hydro, but we know that there are accelerated particles and they can run ahead of the shock and often cause preheating. Do you expect that to make any difference for the instabilities? Or?
It could, but that's the most popular model for how to generate magnetic fields. But the problem is the skin depth, so the distance that you expect the ions to go. You need really super thermal particles to do kind of exotic things, which is plausible, but typically the scale lengths that are kind of most normal are short compared to the hydro scale lengths. So we probably, if we had a really robust, believable model for how much the super thermal particles were affecting the upstream flow, we could include that. Currently we don't. But it's nice, this is a clean hydro model.